Hey guys, welcome back to my channel. I know it's been a long time, and today let's talk about chi-square distribution and the chi-square test. Okay, so what makes chi-square distribution so special? We never talk about any topics of non-parametric statistics, and today is the first one. Okay, chi-square distribution and chi-square test is one of the non-parametric statistic concepts. And you might wonder, why do we need to learn chi-square distribution and chi-square test? Because we already learned normal distribution. It seems like jack of all trades, right? Or it's the go-to for almost everything, especially when we learn essential limit theorem. We know that when the sample size is large enough and the sample means will follow normal distribution. When the sample size is small, we kind of, need to assume that population is normal so that we can use t distribution to correct that z distribution, right? But sometimes if we cannot just assume population follows normal distribution, or if we don't know the distribution of the data follows, or if we don't have any mean to calculate, for example, the variable x is binary, so male and females, we cannot calculate a mean, right? We can only calculate the number of times you observe some specific values. For example, when the variable x is a categorical variable, right? How do we do the test? How do we test whether, two sets of data are the same or different? So in those cases, we tend to use non-parametric test. Chi-square test is one of them. Okay, let's talk about that today. And without further ado, let's dive in. For chi-square distribution, we usually use this Greek letter chi squared to denote. So we call this chi-square variable. Okay, so this chi-square variable is based on a standard normal random variable. For example, if x follows normal distribution with mean 0, standard deviation 1, and we can call the z, right? The variable follows z distribution or standard normal probability distribution. So that's if you randomly select a value of this variable and square it, and this x squared, we call this the variable x squared, it follows chi-squared distribution with the degrees of freedom 1. Here, just a degree of freedom 1. Okay, or we can use z to denote the standard normal distribution. Z follows normal distribution with a mean 0, standard deviation 1. And by convention, we just use z to denote standard normal random variable. So if you randomly select a value of z and square it, and this follows chi-square distribution with the degrees of freedom 1. So at this point, you can tell that chi-squared distribution has only one parameter as a positive integer, this value. Usually we use k to denote. Okay, we use this. We can write this way. If you randomly select two values of standard normal distribution, random variable or standard normally distributed variable, and like say z1, right, follows normal distribution with a mean 0, standard deviation 1, and z2 follows standard normal distribution, mean 0, standard deviation 1, and z1 squared plus z2 squared follows chi-square distribution with degrees of freedom 2. And then you can generalize it. Okay, let me write here. You can generalize it. You can use a letter like q to denote a sum, like z1 squared plus z sub 2 squared plus all the way to z sub k squared. Okay, you can write this way: sum I equals 1 all the way to k, and z sub I squared. Okay, and this whole thing is variable q, can take on different values depending on different values of z. This q is distributed according to the chi-square distribution with the degrees of freedom k. Okay, this is usually denoted as q follows chi-square distribution in parentheses k, or you can write q follows chi-square distribution subscript k here. So again, chi-square distribution has only one parameter, the positive integer k, that specifies the number of degrees of freedom. okay, the number of random variables being summed. Okay, z sub I. How many terms being summed up? K is number of random variables that follow standard normal distribution. x1 squared plus x2 squared. I suppose each value follows standard normal distribution. That follows chi-square distribution with the degrees of freedom 2. And x1 squared plus x2 squared plus x3 squared follows chi-square distribution with the degrees of freedom 3. Okay, and let me show you the graph. You see, I got this from Wikipedia. So that's chi-square distribution, probability density function. So that's probability density function PDF. I talked about that in today's class. PDF probability density function, that's for any value of x you plug into the equation. So for example, when k is 1, and then you get this yellow curve, right? That's chi-square distribution with the degrees of freedom 1. And so that's chi-square distribution with the degrees of freedom 1. You have a functional form. You can write this f of x and subscript k to know the number of standard normal random variables being summed up. Right here, k is 1 in this case. If you have value of x plugged into this formula, you can get the height of the curve. For example, when x is 1, and then the height of the curve is this much. Let me use this color. Okay, but chi-square is a continuous probability distribution, so this is continuous. So the height of the curve is meaningless. So usually we look at the area under the curve within a range to denote the probability that x is in a range. Case 2, you have this green curve, right? That's what the curve looks like. Case 3, this blue curve is positively skewed. In case 4, right, and this dark blue curve. In case 6, purple and red. It looks pretty similar to F distribution, okay? But F distribution depends on 2 degrees of freedom. Degrees of freedom in the numerator and degrees of freedom in the denominator. But chi-square distribution only depends on one parameter, which is the number of random variables being summed, okay? And now let's look at what the relationship between chi-squared distribution and chi-square statistic. Chi-square statistic look like this. Equals sum of observed frequency minus expected frequencies squared divided by expected frequencies. Frequency here means the number of times you observe a success, okay? And how many terms? I suppose n terms. And here, n seems like how many terms summed up, which is different from this k, okay? You understand right away if you understand the things that I'm going to write here. That's, I think, the game changer. Or if you really want to understand the chi-square statistics in a chi-square test, you definitely need to understand this thing. Okay, I'm gonna show you here, which is very simple, which is as long as you know the z-score, how to calculate z-score. So we know that chi-square depends on a standard normal random variable. That's variable x follows standard normal distribution. Okay, suppose we have a variable x that follows normal distribution with mean mu, standard deviation sigma. And we can easily convert it x into a z, right? That follows normal distribution with mean 0, standard deviation 1. And the conversion is just a z-score for x is the value of x minus mean of x and divided by standard deviation of x. Right, so this variable is z variable, or it's a standard normally distributed variable. Follows normal distribution with mean 0, standard deviation 1. And then according to the definition of chi-squared statistics, chi-squared distribution, or chi-square variable, we know that if we squared this, and this will follow chi-square distribution with a degrees freedom 1, because we only have one standard normal random variable here. And now you just need to use your knowledge about binomial distribution. Suppose x follows binomial distribution. You only need 2 parameters, number of trials and probability of success on each trial. So this is a number of Bernoulli trials. check out my videos about Bernoulli process or Bernoulli trials and binomial distribution. And this P is probability that you observe success on each trial. Right? This is a Bernoulli process. And then we know that if X follows binomial distribution, you have a formula, right? Probability mass function, by the way, right? It's like P of X equals N choose X, P to the X, and 1 minus P to the N minus X, right? But we don't need this formula here. What we need is the mean of X and the standard deviation of X. The mean of X or expected value of X, we have our shortcut formula that equals number of trials times probability of success on each trial. And we have a shortcut formula for variance of X also. So that's variance of X equals N times P times 1 minus P, which is N minus P times Q. We use Q to denote the probability that we'll observe a failure on each trial. Okay, that's Bernoulli process. And then we can convert X into a standard normal random variable, assuming number of trials is large enough so that we can use normal distribution to approximate this binomial distribution. Okay, I write it maybe right here. Assume N is large enough, again, we can use the normal distribution to approximate binomial distribution. And then I can convert this X into a standard normal distribution. So that Z now equals value of X minus mean of X, which is N times P, and divided by standard deviation of X. Don't forget, this is a variance, be careful, okay? In a standard deviation, to take square root of this, you can get a standard deviation of X. And then that divided by standard deviation, N times P times 1 minus P. And this follows normal distribution with mean 0, standard deviation 1. Okay, approximately follow this. Okay, just use this follow notation here. And then we squared it. We can square this. And this follows chi-square distribution with degrees freedom 1. So now the kick lies in understanding this part. We can understand this. That equals X minus NP squared divided by NP times 1 minus P. And this equals the numerator X minus NP times N minus X minus, okay, let me zoom out a little bit, N times 1 minus P. So look at what's inside. So this N minus X minus N plus NP. You can cancel out N. You get this negative X plus NP, right? Which is negative X minus NP. And this term equals X minus NP. That makes sense? This whole thing equals X minus NP times NP minus X divided by NP 1 minus P. And then let me do this. So that equals, just focus on the pink part. So that equals X minus NP squared divided by NP plus N minus X minus N times 1 minus P is Q, the probability that you observe failure on each trial, squared divided by N times Q. They are equal. And then look at this. This is the frequency, number of times you observe success, and this is the expected value of X, average, right, is here. And this is number of failures minus the mean number of failures, N times Q, right? And then squared in denominator is the expected value of X, expected value of N minus is a failure, expected value of failure. So you can write this way. That equals observed minus expected squared divided by expected plus observed minus expected squared divided by expected. And Carl Pearson generalize this term. So that equals, by the way, this follows chi-square distribution with degrees freedom 1. I better be consistent with the color. So that's follows chi-square distribution with degrees freedom 1. And Carl Pearson chi-square test generalize the form, right? Generalize the formula. So that's chi-square statistics equals sum of observed minus expected squared, okay, the numerator squared, and then divided by expected. This is how many terms, and this n, you see in this case n is 1, but here n is how many rows in a table. Okay, so n is how many rows. So you can use this to compare two sets of data. So this is observed, and this is expected. You have the frequencies, and you compare whether these two sets of data are statistically significantly different. So the n here is number of rows. Okay, number of cells in the table, number of rows in the table. Okay, I don't want to make this video too lengthy. I'll just try to understand this part. And then this observed frequency, expected frequency divided by expected frequency. They're all frequencies. Okay, I will talk more about this maybe in the future videos and in the next video. Okay, I'll talk more about this in the next video, so stay tuned. Hope you found today's video helpful, and any questions and comments, please let me know. Thank you so much for watching, and see you next time. Bye.